Hello, welcome to the second lecture in the first part of Mathematics for Machine Learning, where we're looking at linear algebra. Today we're talking about linear maps and subspaces. We already said last time that vector spaces can contain other spaces. If V is a vector space, then S is a subspace of V if it fulfills three properties. The first one is that the zero element, the null element, is an element of the subspace. Then that it is closed under addition. That means that if we take any two vectors x and y, then their sum also needs to be in the subspace. And third, it needs to be closed under scalar multiplications. That means that if we take any vector element of the subspace multiplied by a scalar constant, the result also needs to be in the subspace. Now, if we look at these four examples here, then we said that only the fourth one of these is a subspace, because each of those violates one or the other property. For example, the first one, the properties 2 and 3 are violated. In the second one, the property 1 is violated because the null element is not element of the subspace. For the third example, property 2 is violated because if you, for example, take these 2 points here, then their sum will be outside of the subspace. However, the fourth one is the so-called trivial vector space. This is a vector space that only contains 0, and this one fulfills all the three properties of subspaces. A function t that goes from a vector space V to the vector space W is called a linear map. If for all vectors x and y that are element of V, and for all scalar lambda and kappa, t, this function of the sum of lambda times x and kappa times y equals to lambda times t applied to x only and kappa times t applied to y only. If we have such a linear map, T, then this induces two important subspaces. The first one is the null space of T. It's defined as the set of all vectors in V with the property that T applied to these vectors equals 0. So the null space is a subspace of V. And the second important space is the range of T. So the range of T is defined as a set of all vectors y in W, so on the other side, with the property that there exists some other vector x in V such that T maps from x to y. Maybe it would make sense if we draw a picture about this. So we start out by drawing these two vector spaces, V and W. And there is our function T that maps from V to W. Obviously, V has a 0 element, W has a 0 element, and now the null space of T is a subspace of V that if we use T, then we get the 0 back in W. On the other hand, the range of T is a subspace of W. Namely, it's the set of vectors in W that any vector in V maps to. So it goes basically from all of V to the range of T. And also note that because the null space of T is a subspace of V, it obviously contains also the null. And similarly, because the range of T is a subspace of W, it does contain the zero again. Now, linear maps are typically defined by a matrix A. And here we see a number of these matrices and the types of linear maps that they define. So in this example here in A, we see the original data, which is in R2, points placed in an equidistant grid, colored from yellow on the top to blue on the bottom. Now here we see, as an example, the matrix A1, which is a 2 by 2 matrix. So it goes from R2 to R2, which does a rotation by 45 degrees. So it means that it takes this point here and maps it over here. Similarly, takes this point here and maps it over here, and so on and so forth. A different example of such a matrix is A2. So A2 is again a 2 by 2 matrix, so it again goes to R squared, and it only has non-zero entries on the diagonal, which means that it stretches the dimensions but does not do any rotation or anything like that. So there's a 2 in the first dimension, which means that it takes all the points along this dimension and stretches it by 2. So that's why they are now twice as distant in this one. And then there's a 1 on the second diagonal element, which means that the other axis is not changed. And here A3 is another example of such a matrix that defines a linear map. It's now an arbitrary matrix that does a combination of rotation and scaling. And so this original square is now mapped to this shape here, sheared in some way, but linearly, because the 0 always maps to the 0 in each of those points. In this case, we also see that the null space is only given by the null in our original vector space. So the null space is only a single point. The reason for that is that there exists no non-zero vector x that gives us a 0. Similarly, the range is all of R squared for this case. And the reason for that is that all these matrices that we see here, all of these example matrices, are full rank. Because we're working with a matrix A and we can define linear equation systems also based on A, that we can also call the null space the column space of this matrix A. For a set of vectors V1 through VR that are an element of a vector space, we may call them linearly independent if and only if the following property holds. Namely, that if we take a linear combination of them, so it's basically the sum of from I equals 1 through R, some scalar times vi. If this is 0, then it must be the case that those lambdas are actually not arbitrary, but that all of them are 0. Now, what linear independence also means is that we cannot take one of those vectors and represent it as a linear combination of all of the others. So if we move one of those over here, then it needs to be the case that still the lambda here is 0. Let's look at an example. Say you are in Nairobi in Kenya and you would like to describe the way to Kigali, which is in Rwanda. Now you might say, well, in order to go to Kigali, well, you have to first go 506 kilometers northwest to Kampala, which is in Uganda, and then 374 kilometers southwest. Now this is perfectly sufficient in order to describe the location of Kigali in 2D. But you could also first go in this direction and then go in this direction. In fact, with these two vectors you can represent all of r squared. So just by putting different numbers here in the front, you could in principle reach any point in this map just by somehow always going a bit in this direction, then a bit in this direction, then a bit in this direction, and so on. Now let's say this person also adds, well, Kigali is 750 kilometers west of Nairobi. While this is interesting information, in principle it's completely unnecessary because the 2D space is already spanned by these two vectors. For any vector space B, we call some subset of it, so a set of vectors B, a basis of V, if the span of B equals to the vectors. So the space that is spanned by these vectors that can be represented as a linear combination of the elements in B, the individual vectors, equals the whole vector space, as we have seen in our example in 2D. So for 2D we needed a base of two vectors. And the second property that we want is that B is linear independent. So the vectors in the set B are linearly independent. Here on the right side we see two examples of different bases of r squared. So this vector here can be represented as 2 times e1 plus 3 times e2. But it can also be represented as minus 1/2 times b1 plus 5/2 times b2. So these are two representations of the same vector x. Now, we already have seen this example. We said that this is not a subspace of r squared. However, if we moved it a little bit such that it goes through 0, it would be a subspace. And this concept is exactly given by affine subspaces or linear manifolds of our vector space V. So let's define this. Let V be a vector space and x0 be some vector from V. If U is a subspace of V, then L is the space that is given by U displaced by this vector x0. So if x0 is this vector here, and this would be U here, then, and this would be L, we see that L is such a affine subspace. So it's really the set of vectors U element the subspace plus x0. Or it is the set of vectors V in our original vector space for which there is a U in the subspace capital U, such that this vector V equals the sum of x0 and this vector U. Note that this definition also means that L does not include 0 unless x0 is an element of this direction or direction space. And also note that if x0 was an element in U, then actually U and L would be identical. In machine learning, we typically use affine subspaces to define hyperplanes. And these hyperplanes we usually describe by parameters. Now, if we have some ordered basis of this subspace U, this direction or direction space, then every element X of this affine subspace L can be uniquely described as the sum of x0 plus a linear combination of the spaces. Now let's summarize this video. We talked about subspaces. A subspace S, which is a subset of V, is a subspace if it contains the null element, if it is closed under addition, if it is closed under scalar multiplication. Subspaces can be induced by linear maps, which again can be represented by matrices. A subset B, so a set of vectors B, is a basis of a vector space V if it spans all of V, so the span of B equals V, and its elements are linearly independent. So the vectors in the set are linearly independent. Finally, an affine subspace V is a subspace U shifted by a support point x0. So L equals x0 plus U. And with this short introduction to subspaces, linear maps, and affine subspaces, I want to conclude and see you next time. Bye bye.